Hello, everyone. Welcome back. We are going to be talking about enzymes part 2 today. So we're still discussing enzymes. Remember, enzymes are a protein, and we're going to continue to delve into the topic today. So many enzymes end with the suffix ase, as I mentioned last video. So some examples that you might hear are lipase, maltase, protease, and lactase. And they act on whatever the first part of the word was. So if it's a lipase, it acts on lipids. If it's a maltase, it acts on maltose, which since you recognize that ose, that should tell you that's a sugar, therefore a carbohydrate. Protease acts on proteins, and lactase on lactose, which again, ose, sugar, carb. And we talked about how enzymes lower the activation energy and therefore accelerate the chemical reaction. There is also other factors that it depends on, and that is the temperature, the pH, and the concentration. Those are the three key factors that will determine the rate of the reaction. The temperature is very important. There's something called an optimal temperature, and that is the exact temperature at which the enzyme will be able to decrease the activation energy. So if you go over that optimal temperature, the enzyme's activity will decrease. So we don't want to go over that optimal temperature. The optimal temperature is like the ideal temperature. Your pH is also very important. Well, not yours specifically, but the pH of the reaction. We use something called hydronium ions, and that's just H+. That is going to be helping determine the pH of the solution. So whenever you see those little strips of paper or any kind of measurement for pH, that's what is being used normally. And the pH does alter the enzyme activity. So if it has too much pH, too high of a pH, it's too basic, or too low of a pH and it's too acidic, the enzyme can vary in activity. So again, if you don't remember, for a pH scale, the bases are the ones that are higher up and the acids are when they are lower down. Remember, 7 is the neutral amount. Some examples of bases include sodium hydroxide, potassium hydroxide. Some acids will be things like hydrochloric acid or sulfuric acid, which are those equations there. As you can tell by the little animation, the H is what tells you that it's an acid. If you see H followed by some other elements, that hydrogen at the beginning, it's letting you know that's probably an acid. HCl is the most common one, but there's many, many acids. So some real world examples of these include, for example, stomach fluid, the chemicals in your stomach, the acid literally breaking down the food that you eat. Lemons are another great example of acids. Vinegar, anything kind of soury tasting, is usually an acid. Bases are the opposite end of the spectrum: milk, baking soda, tea. So for example, you know, when you have an upset stomach, sometimes your parents will tell you to drink a specific tea because it has basic properties, and so it's able to calm down the acids in your stomach. Or something very common, at least in my family in Mexico, this was very normal. They would tell you to take baking soda, like a little pinch of baking soda, if you had like upset stomach or something like that. And that's again because of its basic properties. The concentration of the enzyme is also very important. The rate of action will depend on that as well. The larger the concentration of the enzyme, the faster it will work. However, there's also an optimal range. So there's a specific amount that we want to have of an enzyme for it to work at its best. Its ideal conditions are those optimal concentrations, optimal temperatures, and optimal pH. Sometimes it will be very common for you to see graphs like these showing you different levels of substrate concentration in comparison to the reaction rate. So the more substrate you have, right, the more it increases, the reaction rate also increases, so it moves faster. The optimal enzyme concentration is when that line turns flat. And so that's when you see that's basically the maximum level that you can go to. And once you go past that, there's not really much of a difference because it's saturated, right? It's at its maximum capacity. That means there's way too many substrates for the amount of enzyme. And so they're just kind of waiting in line until enough substrates leave or products leave for more substrates to be able to take the place in those enzymes. Now there is a process called denaturing. That is when something is not at those optimal measurements, right? So if it's, for example, for pH, if it's too acidic, or if it's too hot in temperature, or there's too many substrates, right? If you go over the limits, that can cause the enzymes to kind of change. That's denaturing. It's when you see a change in the shape of the enzyme. And so now the active site is no longer the ideal shape for those substrates to come in and either perfectly fit, like in the lock and key model, or wiggle themselves in, like in the induced fit model. So now the enzyme is so just warped that the substrates aren't able to fit, and that is not going to allow the enzyme to function properly. So think of a person, you know, if you have a high temperature, if you have a fever, you are not able to, you know, see properly. You're going to be all sweaty and not able to function as you normally would, right? The same thing happens to the enzyme. It gets too hot and it starts kind of shifting its body. It starts looking different. So instead of you just laying down in bed and drinking, you know, chicken soup until you feel better, the enzymes actually warp. So imagine if when you had a fever, you warped into something else. So instead of being human, let's say you warped into a snake, right? That's essentially what's happening to the enzymes. You're not changing into a snake, but, you know, changing shape. And that is causing the substrates to not be able to fit, and therefore the enzyme's pretty much useless now. So that's why we're trying to keep everything at that optimal range, the ideal situation. Now there's also something called enzyme inhibitors. So to inhibit means to hinder or to block the ability to do something, right? To damage something in some way, to do the opposite of fixing, right? To block something, to change it, to alter it in some way. So in enzymes, the inhibitors work kind of as a duct tape that goes over your active site and binds to it, and now it's competition for the substrate, because if the inhibitor comes in and binds to the enzyme, it's now taking up the place that a substrate could be taking up. And it's slowing down the process of the enzymes. It's blocking the process of the enzymes speeding up the chemical reactions for the substrates, because now they have to wait a little longer because a lot of enzymes are being taken up by the inhibitors that don't actually need a chemical reaction to happen. So they slow down the process and they're blocking the path for other people. Think of if you have to go to like the supermarket and buy something, and then there's people at the checkout line that are just waiting there while, sometimes there's like the parents that leave the kids in the carts and just to like hold their spot while they still are shopping in the grocery store, and you're like waiting behind the cart and trying to be a good person and not skip ahead because you see the kids there. Yeah, it's slowing down the process for you and everybody behind you. That's kind of the enzyme inhibitor idea. And that's it for this video. Let me know if you have any questions during class, and I'll see you then. Okay, fine. And I'll see you then. Bye.